Alright friends, welcome back. In this video I'd like to cover section 3.4 of your textbook, and we are going to continue to talk about zeros of polynomials in this video, but we're going to move on by taking a look at polynomials that unfortunately we're not going to be able to factor. So we have found zeros of polynomials before, but they were able to be factored, and so in this video we're going to specifically focus on a method that you can use to find those zeros, but without having to factor your polynomial, because you can't always do that. And so it turns out that what we need for that is a couple of algebraic theorems, right? So we're going to start off with the fundamental theorem of all of algebra, which is going to have a small application to what we're going to do here in this process. Basically, this theorem is going to give you an idea of how many zeros you should expect to end up with after you do the whole process, right? So it says here that a polynomial with degree n has exactly that many zeros, okay? So if you have a degree 2 polynomial, you should end up with 2 zeros. A degree 5 polynomial, you should end up with 5 zeros. But one of the special things that we need to make sure that we point out here is two things, actually. First of all, that some of those zeros may be complex numbers. So we could have a combination of real and complex numbers. Those would contribute to the n zeros that we may have. And also, the other thing is that this is going to include what we refer to as repeated zeros. Okay, and so we've talked about repeated zeros before, and we'll see an example a little bit on in the video where we're going to have an example of a repeated zero, but that's just an example of a zero that shows up more than once, of course. So we'll see that a little bit later on. Okay, so that'll give us an idea of how many zeros we should expect to end up with in our process here. So just to get some practice with that, again, whatever the degree is, that's how many zeros you should expect to end up with. So in the case of number 1, where we have a linear, the degree is 1, we should end up with that many zeros, which is 1. In the second one, we have a quadratic. The degree, of course, would be 2, and so that means that's how many zeros we should expect to end up with here. And it's the same thing all the way down. So if we have a degree 4 polynomial, we should end up with 4 zeros. A degree 3, we should end up with 3 zeros. Just don't forget that this includes repeated zeros, and this also includes complex zeros in this list here as well. Okay, so once we have an idea of how many zeros we should expect to end up with, what we need to do is compile a complete list of all the different possible zeros that are out there, right? So I like to kind of explain this as you're hiring for a job, and what you're going to do is compile a list of resumes of people applying for that job, and then you're going to go through the process of figuring out who is actually going to get the job and who's not, right? So this is us basically putting our candidates together, our big pool of candidates, right? So if we have a polynomial, which you guys hopefully by now are familiar with the form of a polynomial, one of the more important things here is that we need to have integer coefficients, okay? So specifically, we need the leading term to have an integer coefficient, and we need our constant term to also be an integer. And just to remind you, an integer is any number in this list from all of your negative counting numbers to 0 to all of your positive counting numbers, okay? So no fractions, no decimals. What we're going to do is we're going to compile a list of possible candidates by making fractions out of the factors of your constant over factors of your leading coefficient, okay? So whatever those numbers are, assuming that your polynomial is written in standard form, we're just going to have to take a look at that number all the way in front, take a look at that number all the way in back, find the factors of those, and then make fractions out of them, okay? So as an example of that, let's go ahead and take a look at example 2 here, where it says list all the possible rational zeros of this function f of x, and then check which zeros are on the graph of f. So let's go ahead and do that here real quick. Pointing out our constant and our leading coefficient, looks like playing the role of our constant here is going to be a -6, and then playing the role of our leading coefficient is going to be the number sitting in front of the x to the 4th term, which of course is just simply a 1, okay? So if we were to go ahead and put those fractions together, these rational numbers here, these of course would be factors of -6 over factors of +1. Let's just brainstorm on what those would look like, right? So factors of -6. Well, of course we would have positive or -1, positive or -2, and 3, and 6 itself, okay? So the positive or negative version of any of those numbers, those are all factors of -6. The only factors of 1 are going to be positive or -1. So that means when we look at all the different combinations of a number on top, of which there are 8, keep in mind, because you have the 4 positives and the 4 negatives, combinations of those 8 numbers on top over those 2 numbers on bottom, we would end up with this list right here, either positive or -1, basically all the ones that were originally on top, since we're just dividing by 1 here. And we would get this pool of candidates. So that is 8 people applying for the job to be a zero of this polynomial function, and that's all they wanted us to figure out here in this example, so we'll just go ahead and box this. Now, it's only going to be the case that some of these applicants are actually going to get the job of being a 0 of our polynomial. And so right now, before we get into the other parts of the process here, we can go ahead and take a look at the graph, which I already have prepared here. And we can see that we cross the x-axis in these two locations. So we cross here at -1, and we cross here at +2. And those would be candidates that live in my list right here. So -1 and +2, these would be the actual zeros of this polynomial, or in other words, I should say the real zeros, because remember, if you look at the degree of this polynomial, it was a 4. And so that means that we have 2 real zeros, but then the other 2 are going to be imaginary or complex zeros. Okay? So the total number of zeros should always add up to the degree of the polynomial there. That's the fundamental theorem of algebra. Okay? And so now I'd like to go ahead and put this all together by doing an example where we are finding all of the real zeros of this polynomial f of x right here. And I do have it graphed for us to be able to kind of check our answer later on, but I do want to go ahead and demonstrate that process of how we would go ahead and find all of these real zeros here real quick. So we're going to start this off by first acknowledging that we have a cubic polynomial here, and so that is how many zeros we should expect to end up with at the very end of this process. Okay, keep in mind that's both real and complex, so the number of real zeros we end up with is either going to be 3 or something less than that. Okay, and now what we need to do is just go ahead and compile that list of possible candidates here. So we need to do factors of our constant, which is +3, over factors of our leading coefficient, which here is going to be +2. And so factors of 3, of course, you have ±1. You also have ±3. Factors of 2 on the bottom, you have ±1. And you also have ±2. Okay, so what we're looking for, again, is to write out a complete list of all the combinations of a number on top over a number on bottom. And if you do that correctly, you should be ending up with the 2 numbers on top over 1, and then the 2 numbers on top over 2. So ±1/2, ±3/2. Okay? So just all the combinations there. And it looks like we have compiled a list of 8 candidates that are applying for this job of being a 0 for our function. Okay? And so now we need to go through that interview process and figure out which one of these is actually going to get the job. And by interview process, I mean what we're going to do is we're going to go ahead and use some synthetic division. Okay? Because if any one of these are zeros, then remember the reasoning from the last video is that if we have a 0, of our polynomial that looks like, say, x is equal to some number a, then that always corresponds to an algebraic factor of our polynomial looking like x minus a. Okay, so if we find that we have a number in this list that's actually going to work and be a 0 of our polynomial, then that's going to correspond to a factor. And the thing about it being a factor is that that factor is going to divide into our polynomial evenly, which means that we're looking for a remainder of 0. Okay. So that's what we're going to do. We're going to do some synthetic division just because synthetic division goes very, very quickly, and that is the way we're going to test each one of our zeros. We're looking for the first one in this pool of 8 candidates that's going to give us a remainder of 0 whenever we do synthetic division. So let's go ahead and give that a shot. I'm just going to start at the top of my list here, maybe start with that +1, right? So I'm going to go ahead and start with +1 here, and we talked about synthetic division in a previous video, so I'm not going to go through all the little subtle nuances of doing synthetic division. I'm just going to go ahead and write out what we would get as our result here. So drop the first number, and then multiply, and then add, and then multiply, and then add, and then multiply, and then add. And looky there. We're pretty lucky that way, right? The first candidate that we tested gave us a remainder of 0. That's not always going to happen. If you ended up with a remainder that was not 0, then you would have to throw that 0 out. That is a 0 that did not get the job, and then you would have to test the next candidate, right? But here we have a remainder of 0, so we now know that x equals 1 is going to be a 0 of this polynomial, which of course means that we have an algebraic factor of x minus 1 in our factorization of this polynomial here. Okay, so we can go ahead and write this out. We can go ahead and say f of x was that cubic polynomial from before, but we can now go ahead and write that as x minus 1 times this expression right here. Remember that this quotient, this is what's left over after you divide out an x minus 1 here. So we're going to write that out as 2x squared plus 5x minus 3, and you will find that that is a polynomial that can continue to be factored. So we might have x minus 1 there, and then we can factor this trinomial into the product of 2 binomials. Again, I'm not going to dive too deeply into why the factorization is this right here, because we've talked about factorizations a lot in videos of the past, okay? And so from each one of these factors, zero product property says that we're going to get a 0 from each one of these. So there is the one that we tested and found that worked. But we also find that we get these other two zeros here. By setting this equal to 0 and solving, we get 1/2, and we also get -3. And so these represent the zeros that we have here of this polynomial. And just keep in mind here that we said fundamental theorem of algebra from the very beginning of the problem. The degree of this polynomial was 3, and so that's why we said we should have that many zeros at the very end of our process, and that is exactly how many zeros we ended up with. We can even check graphically on the graph. If we were to graph this here, we have one of these zeros here at -3, okay? And then we also have another 0 here at 1/2 and another 0 here at +1. Okay, so we know we can visually check to see that we do cross the x-axis in these 3 locations. So that's pretty good. Okay, so a lot of different ways you could be able to check your answers here, but again, you're just looking for the first candidate in your pool of candidates that's going to give you a remainder of 0, and then you're going to write it out as a factorization and then just use your usual factoring methods to get the rest. Okay, so let's see that one more time here. So example 4, we have this polynomial. Again, that's not something that we can factor using our previous factoring methods, so we're going to go ahead and use this new process of trying to create this pool of candidates and then test each one, right? So we are looking for factors of our constant, which in this case is a +20, over factors of our leading coefficient, which here is just simply going to be +1. Now, there are a lot of factors of 20, okay? You have positive or -1, you have positive or -2, you have positive or negative, not 3, positive or -4 I meant, and then 5, and then 10, and then 20. A lot of different candidates there. So we need to go ahead and do all the combinations of a number on top over the factors of 1 on bottom, which since that's just 1, we're just going to go ahead and look at this as our pool of numbers right here. Okay, so that is a complete list of 12 different candidates applying for this job. And if you look at the graph, we only cross the x-axis in 2 different places. And you could definitely take a look and see here what we're going to end up with here, right? That's going to be -2, and that's going to be -5 as the only 2 candidates from this list up here that are going to actually get the job at the very end. But we can't just look at the graph and make that determination. We have to go through the algebra and actually prove this, right? So again, just to kind of save some time, since I know that -2 is going to work, I'm just going to demonstrate really quickly that that would be one of the zeros that is going to give you a remainder of 0 here. So just writing out the coefficients and the constant of our original polynomial. Going ahead and doing the synthetic division here really quickly, we would drop the 1, and then multiply, and then add, and then multiply, and then add, and then multiply, and then add. And then, of course, we get that remainder of 0 there. So that's pretty good. So we now know that we can go ahead and write f of x as the algebraic factor that came from the 0 of -2 was x plus 2, of course. And then times the leftovers there, that would look like x squared plus 7x plus 10. Again, just using the coefficients of my quotient there, okay? And now the x squared plus 7x plus 10, that is something that we can go ahead and continue to factor here. So x plus 2 times x plus 2 times x plus 5 would be the factorization there, okay? Now, one of the things that I want you to realize here is that whenever we use 0 product property and get our zeros here, we end up with a 0 of -2 twice, okay? And so what we would do is we would call this a repeated 0. Okay, so remember when we talked about the fundamental theorem of algebra before, we said that it counts repeated zeros. Okay, so we did end up with 1, 2, 3 zeros, which makes sense because we had a cubic polynomial, but one of those 3 is a repeated 0. And so we would just go ahead and say that I've got these 2 zeros here. And I want you to take a look at the graph and see what happens there. Because we had a repeated 0 of -2, we see here that the graph is going to touch the x-axis at -2, but in a little bit of a quadratic way, right? It kind of looks like we have a little mini parabola sitting there. So we would say that we cross quadratically in this case, okay? And that's just because, again, if you look back at the factorization, one other way that I could have written this would be x plus 2 to the power of 2, since I had 2 copies of it, and then times x plus 5. So if you remember that whole business about multiplicities of your zeros, we would say here that -2 has a multiplicity of 2, and that's why we would bounce off of the x-axis in this place, okay? And we would cross through -5 linearly because we just have 1 copy of x plus 5, okay? So that would be a complete problem there. Let's take a look at another example here. So example 5. So one of the things that I want you to really pay attention to here is that in this polynomial, in the standard form, we're actually missing terms, okay? So we go from the x to the 4th term straight to the x squared term, straight to the constant. We're missing our x to the 3rd term, and we're also missing our x term. So just remember a little bit later on that we're going to have to really make sure that we include some placeholders for these terms that we're missing here. So I'm going to say plus 0x to the 3rd minus 17x squared plus 0x plus 4. So any term that you are missing, we're going to have to introduce a placeholder for. That's, again, going to come into play whenever we do the synthetic division, okay? And so creating that pool of numbers here really quickly, right, we're going to have factors of, it looks like 4. So factors of 4, that's our constant, over factors of the leading coefficient, which in this case is also 4. So we have all the different factors of 4, so plus or minus 1, 2, and 4, over all those very same factors. So plus or minus 1, 2, and 4. So all the combinations of a number on top over a number on bottom, we would end up with the following list of candidates. We would have plus or minus 1, plus or minus 2, plus or minus 4. We would also have plus or minus 1/2, and then plus or minus 1/4. Okay, so those are all the different combinations of a number on top over a number on bottom. And again, I am accounting for setting up some fractions and then reducing them. So you may want to take a minute and pause the video and see if that makes sense to you, why that would be our candidate. Or sorry, our pool of candidates, I should say, okay? And then, of course, if we take a look at the graph here in this example, we see that we cross the x-axis in 4 different places. And it looks like one of those places is, of course, here at +1. And that gives us this idea that if we were to go ahead and test +1 using synthetic division, then it would work out for us. And then just, again, don't forget, we need those zeros as placeholders for terms in the standard form that we are, of course, missing here. So just to demonstrate that this will work out for you, we would go ahead and drop the 4, and then multiply, and then add, and then multiply, and then add. Actually, am I making a mistake here? Actually, that is not 1, is it? I made a mistake. That's what I'm thinking here. This is not 1. That's actually going to be +2. I failed to remember that I have the grid going over 2 notches there. Okay, so instead of testing 1, we'll test 2. I'm sorry about that. There we go. Okay, so drop the 4, and now multiply, and then add, and then multiply, and then add, and then multiply, and then add, and then multiply, and looky there, we get a remainder of 0, which is what we were looking for, right? So we know that x is equal to 2 is a 0, which means that we know that x plus 2, or sorry, I should say x minus 2 there, shouldn't I? X minus 2 is an algebraic factor, and that leaves left over 4x to the 3rd plus 8x squared minus x minus 2. Again, if you need to brush up on your synthetic division, I would recommend that you watch the previous video for that. But this is something that you can now continue to factor by grouping, okay? And so if we were to go ahead and do that, we would end up with the factorization x minus 2 times x plus 2 times 4x squared minus 1. Okay, and again, I'm not going to get too bogged down with the factorization there. We've talked about plenty of videos where we have done some factoring, so I'm just going to give that away. And then you'll notice that the 4x squared minus 1, that is a difference of 2 squares, so we can continue to break this up. X minus 2 times x plus 2 times 2x plus 1 times 2x minus 1. In which case, you would see here that we get 4 separate zeros. We get x is equal to +2, x is equal to -2, x is equal to -1/2, and x is equal to +1/2. And that is exactly where we are crossing the x-axis in this example when we look at the graph. Okay, so at those 4 different locations, and again, that makes sense because we had a degree 4 polynomial, so we should expect to have 4 different zeros here. And it turns out that these are all 4 real zeros. Okay, so that's the basic process there. You create your pool of candidates, and then you keep testing them until you find the first one with a remainder of 0 on the synthetic division, and then you just continue to factor the rest using your usual methods. Okay? Since we've seen a lot of examples with real zeros so far, let's go ahead and jump to some complex zeros, right? So one of the key things that we need to always remember is that if you are given that you have a complex zero, then automatically its conjugate is also going to be a 0 of that polynomial. So remember what a conjugate is, right? So that's right here. If a plus bi is a complex number that we give to you is a 0 of your function, then the conjugate of that, which is just the same exact complex number but with a minus instead of a plus, that's also automatically going to be a 0 of your function. So this is going to kind of create problems where I can give you an exercise where I hand you a complex 0. It's just going to have to be one of those things where you always remember that if I ever hand hand you one complex zero, I'm really handing you two, because remember that a complex conjugate is also going to be a zero of that polynomial. So it just is a really basic, easy multiple choice question, right? I could hand you something like this, where it says, given that one of the zeros of this polynomial is 3 plus 2i, which of the following is also a zero? Well, of course, because this already has a plus, we would be looking for the one with a minus, and of course that's going to be choice number C here, okay? And again, we call that the complex conjugate. Okay, so that's just something you will need to remember whenever you're doing problems like this, is that we always are going to have the complex conjugate as well. Okay, so the last couple of examples here in the video, example 7, it says use the given zero of 4i to find all the zeros of this polynomial. Okay, so I'm giving you one of the zeros of this polynomial. It's a complex zero. It's 4i. You need to use that to find all of the different other ones here. Okay, so remember that 4i can be written in standard form as 0 plus 4i, which means that you automatically have another zero here as well, right? So we'll make a complete list of all the zeros that we know. We have 0 plus 4i, and we also automatically know that we have its conjugate as well, right? We have 0 minus 4i. And of course, I'm not going to write these like this whenever I move on. I'm just going to go ahead and write this as 4i, but then this over here, that would be negative 4i, okay? And so, keep in mind what we've said before in the past, right? If we have these zeros, then these correspond to algebraic factors of this polynomial, okay? So in the case of the 4i, that would look like x minus 4i. And in the case of the negative 4i, it would have x plus 4i, okay? And this is actually going to be the way that we're going to come up with the entire function formula here, okay? Because so far we know that our f of x from before, which keep in mind f of x was this big cubic polynomial up here, we now know that it's going to have these two algebraic factors. We can now begin to write this as x minus 4i times x plus 4i, and then times something else, okay? Let's go ahead and figure out what this is going to be actually, right? You may recognize this as the difference of two squares, okay? So when you multiply this out, this is something that looks an awful lot like u minus v times u plus v. And if we have that form, remember, then we can always go ahead and write that as u squared minus v squared to go ahead and figure out what that would factor into, or sorry, expand out into. And keep in mind, you could also do FOIL method for this as well, but this goes a little bit quicker. X squared minus 4i squared is what this is going to turn out to be. And if you do the math on that, remember 4 squared is 16, and I squared is negative 1. So this is going to be x squared minus negative 14, or in other words, it's going to be x squared plus, I think I said 14 a second ago. I'm sorry, I meant 16. There we go. So we're going to have that times something, keep in mind, okay? And now it's our job to figure out what that something is going to be, because right now we know that f of x can be written in this way. We have x squared plus 16 times something. And so in order to figure out what that something is, let's go ahead and do this. Let's do some long division. We're going to go ahead and do some long division. We're going to take our x squared plus 16. I'm going to write a placeholder for my missing x term and say plus 0x. And I'm going to go ahead and divide that into the polynomial that I was originally given, right? So that's going to be a negative x to the third plus 2x squared minus 16x plus 32. If I figure out what the quotient is going to be here, that is exactly what our missing factor is going to be down here to write out my complete f of x. So let's just go ahead and figure this out here really quickly. I'm just going to blaze through this here really fast, right? So we want to match up a 3-term times a 3-term. And so in order to do that, we're going to go ahead and compare the first terms of what we've got. So the first term of my divisor, first term of my dividend, it looks like I'm missing a coefficient of negative 1, and it looks like I'm missing an extra copy of x there. So if I distribute that to all my terms, I'm going to end up with negative x to the third minus 0x squared minus 16x. And of course, we are subtracting here. So when we subtract all those different rows there, we're going to end up here with positive 2x squared. And then that's going to make a 0x there. We're going to drop down our 32, so we're looking at 3 terms there. And then, of course, we're doing that whole comparison game all over again. Now, the only thing that we're missing is an extra copy of 2. So if we distribute that 2 inside there, and again, if you need more review over your long division, then check the previous video. But you'll see here that when we go ahead and introduce that, all of these columns are just going to reduce down to 0. And so that, of course, is going to be our remainder after the long division. So we know that this divides evenly. So one of the things that I now know is that my polynomial can be written as x squared plus 16, but now times negative x plus 2, okay? And so in which case we would see that we get the following zeros from this, right? So f of x is equal to the x squared plus 16 times negative x plus 2. in which case we get the plus or minus 4i that we said from the beginning. But we also see here that we get a real 0, and if you were to set that equal to 0 and solve, you would see that that just ends up being positive 2, okay? So we ended up with 2 complex zeros, and we ended up with 1 real 0, and so that means 3 zeros total, and that does make sense because we did have a cubic polynomial to start. Remember, the fundamental theorem of algebra says the number of zeros should be equal to its degree always, okay? And then it says here in example 8, this will be the last example that we do here in the video, it says to write f of x is equal to x to the 4th minus 81 as a product of linear factors. So what does that mean, linear factors? That just means simply, of course, a factor that looks like x minus some number. You could also say x plus that number, in which case we would interpret that number as a negative, right? And then find all the zeros, right? So here we go. So one of the things that we might want to do here is investigate the x to the 4th minus 81. There are a couple of flags here that clue you into why this would be one of those classic factoring formulas that we talked about earlier, right? So some flags here are the fact that I've got two terms, I've got a minus sign in between them, so that's a difference. I've got a number like 81, which is a perfect square number, and then I've got an exponent of 4, which is also a perfect square number. So these are all red flags for you to be able to kind of tell that this is of the form u squared minus v squared, okay? In which case we can go ahead and do some work and figure out what's playing the role of u and v. So playing the role of u, I think there would be an x squared. Playing the role of v, I believe there would be a 9. Okay, so this really is a difference of two squares, and now that we've recognized that form, we could go ahead and factor this up into u plus v times u minus v. Okay, and so playing the role of u, of course, we said from before, is x squared. Playing the role of v is 9, so we're going to have x squared plus 9 times x squared minus 9, and that's equal to 0. Okay, so knowing your factoring formulas is very, very important here. Okay, now, we need these to be linear factors. And so what that's going to mean is that we now need to continue to look at this as a difference of squares, right? So each of these individually can be rewritten as this is x squared minus negative 9 here in this case. And this is, of course, x squared minus 9. These are both individually differences of two squares. We would simply have here x plus 3i times x minus 3i times x plus 3 times x minus 3, okay? So again, where am I getting these from? Well, the idea is I'm getting these from, if I take a look at this as a difference of two squares, then that is going to give me this factorization. I'm just applying that whole difference of squares formula that we saw from before. And then, of course, this right here, x squared minus 9, factoring that, I'm going to get this factorization right here, okay? So these, again, are all linear factors. They all say x minus or x plus some number. And from this, we can go ahead and get all of these zeros listed out here, okay? So x is equal to negative 3i, x is equal to positive 3i, x is equal to negative 3, and x is equal to positive 3. Okay, so these represent the 4 different zeros of this polynomial, and it makes sense that we ended up with 4 here because the degree of our polynomial initially was 4. Okay, so again, just a whole bunch of difference of two squares formula coming into play to factor this polynomial and get all of these zeros from that. So I hope this video has been of some help to you. Please remember that if you have any questions whatsoever, I'm always happy to answer those, so make sure to let me know if you do. And yeah, that's all I have here for this one. Thank you very much for your attention, and I'll speak to you guys in the next one.